Hello. In this video, we are going to derive the stretches and bends of the molecular vibrations of the nickel tetrachloride dianion. Recall that this particular ion, having nickel plus 2 at the center, is a square planar molecule. Therefore, it belongs to the point group D4H. The first step in the Kim method is to supply coordinates for each of the symmetry identical atoms in the molecule. And we see that each of the 4 chlorine atoms is symmetry equivalent because we can transform one chlorine into another by using a C4 or a C2 or a mirror. So there's at least one symmetry operation which will transform the chlorine into another chlorine. So therefore all 4 chlorine atoms are symmetry equivalent. And we construct coordinates using something like a unit square, starting at the origin, and using this direction as the x-axis. The coordinate for the first chlorine atom is going to be 1, 0. For the second atom, going in the y direction, the coordinates are going to be 0, 1. Third, for the third chlorine atom, we can represent that by the coordinates -1 and 0. And for the fourth chlorine atom, we use the coordinates 0 and -1. We can think of the bond connecting nickel to the first chlorine atom, for example, as a vector, starting at the nickel atom and ending at the chlorine. And we'll denote this particular vector as R1. Similarly, the vector connecting nickel with this chlorine atom we will refer to as R2. The vector connecting nickel to the third chlorine atom we will refer to as R3. And last but not least, the bond connecting nickel to the chlorine here will be referred to as R4. Next, we look at the character table for D4H, and we notice that for the irreducible representation A1G, the totally symmetric representation, that it has a basis function x squared plus y squared. The way we use that within the Kim method is that we substitute the values of these coordinates, the x or the y value, into this basis function, and this becomes the coefficient of the vector. So for example, for R1, the x value is 1 and the y value is 0. X squared ends up becoming 1, y squared is 0, 1 plus 0 is 1. So the coefficient of R1 is going to be simply 1. Similarly for R2, x is equal to 0, y is equal to 1, so x squared plus y squared is going to equal 1, so the coefficient of R2 is also going to be just 1. For R3, x is equal to -1, y is equal to 0, x squared plus y squared, for those particular values of x and y, gives us a value of 1. That is the coefficient of R3, so we have plus 1 R3, which we just write as plus R3. And for R4, x is equal to 0, y is equal to -1, x squared plus y squared, using those particular values of x and y, gives us 1. That is the coefficient of r to the 4th of R4. So our molecular vibration here, the stretch is going to be R1 plus R2 plus R3 plus R4. The next irreducible representation that we're going to look at is B1G, and we noticed in the character table for the group D4H that the basis function for B1G is x squared minus y squared. So again, using each of the vectors R1, R2, R3, and R4, we find the appropriate coefficient by substituting the values of the coordinates, the x and y values, into this basis function, and that becomes the coefficient. So for R1, x is equal to 1, y is equal to 0. So x squared minus y squared is again going to be equal to 1. So the coefficient of R1 is going to be 1. Now we get something more interesting because with R2, the value of x is 0, but the value of y is 1. So now the value of x squared minus y squared is minus 1. So the coefficient of R2 is going to be minus 1. So we have R1 minus R2. For R3, x is equal to minus 1, y is equal to 0. So x squared is equal to 1, minus y squared is 0. So this gives us a value of, again, 1. Our coefficient of R3 is going to be a plus 1. So we have plus R3. And for R4, x is equal to 0, y is equal to minus 1. X squared minus y squared, with those particular values of x and y, gives us minus 1. So the coefficient of R4 is going to be a minus 1. So that gives this particular molecular stretch as being R1 minus R2 plus R3 minus R4. We will show this in more detail later, but we think of a positive coefficient as being an increase in the length of the bond and a minus sign being a decrease in the length of the bond. So as R1 gets bigger, R2 gets smaller, R3 gets bigger, R4 gets smaller during the B1G molecular vibration. For our last stretches, we need the irreducible representation EU, which is a doubly degenerate representation, and we can recognize that in the character table because we see this parentheses x comma y, which looks like the way we write an ordered pair in Riemann 2-space, good old R2, the plane, but this is actually telling us something different. It's telling us that the basis functions for EU are x and y, and this is doubly degenerate because we see two different functions inside the parentheses. So within the Kim method, we can actually determine each of the two doubly degenerate representations independently of each other, which is a very useful feature of the Kim method. So let's first see what we get if we use the basis function x. So for R1, the value of x is 1. So that's the entire function here is just the x coordinate. So since the x coordinate is 1, the coefficient of R1 is 1. So it just gives us R1. Now we see for R2, the coefficient of the value of x is 0, so the coefficient is equal to 0. So we have 0 R2, we have no R2 term. For R3, the value of x is now minus 1, so the coefficient is minus 1. So that gives us R1 minus R3. And for R4, we see again that the value of x is 0, so therefore we substitute that into the basis function. The basis function becomes 0, therefore the coefficient of R4 is equal to 0. So the entire molecular vibration here is R1 minus R3. Secondly, we look at the other member of the other pair, which is the y basis function. So now we look at the y coordinate. So for R1, the y coordinate is 0. Therefore, the coefficient of R1 is also 0. For R2, the coefficient is going to be equal to 1 because the value of y is 1 for that particular point. So that gives us R2. For R3, the value of y is 0, so the coefficient is 0. And then for R4, the value of y is minus 1, so therefore the coefficient is minus 1 for R4. So that gives us the pair of doubly degenerate representation vibrations, R1 minus R3 and R2 minus R4. Next, we want to derive the bending vibrations. And a way to represent a bend is to think of a vector that bisects the angle chlorine, nitrogen, chlorine for this particular bond. And we often refer to this as B1 for a bending motion. And we can define the bond angles similarly by these bisecting angles. We refer to them as B1, B2, B3, and B4. And similarly to what we had done for the stretching vibrations, we can also plot these particular vectors as points on a unit square, starting at the origin, where B1 is this vector going to the point 1, 1. For the bending motion B2, we're going to the point -1, 1 for B2. The vector here, this is B3. The coordinates of this particular point are going to be -1 and -1. And last but not least, we have the last bending motion, B4, this bisector here, and we refer to this by the points 1 and -1. Now, one question you might ask is, why don't we swap the diagrams that we've used of the bending motions and the stretching motions? Why do we pick the stretching motions so that they went exactly along the x-axis? Well, the reason for doing that is within the character table for the group D4H, it is set up to properly label the irreducible representations so that one of the C2s goes directly along this particular chlorine-nitrogen-chlorine bond, this straight line here, and this is the x-axis. So we're using the traditional nomenclature to define where the particular symmetry operations are for the molecule, doing the stretches first, and then we, using the same system, we used the similar coordinate system to define the bends. The first bending motion we want to look at is that corresponding to the irreducible representation B2G, and we notice that the basis function listed in the character table for B2G is xy. So x times y. So we substitute the values of x and y that we selected for the coordinates here into this basis function, and that becomes the coefficient for the bending motion, either B1, B2, B3, or B4. So we notice for B1, x and y are both equal to 1, so x times y is equal to 1, so the coefficient of B1 is simply 1. Now for B2, x is -1, y is +1, xy is now -1, so the coefficient of B2 is -1, so we get a minus B2. For B3, x and y are both -1, we multiply them together, we get a +1, so the coefficient of B3 is a +1, so we get plus B3. And then the last one, we have x is equal to 1, y is equal to -1, so xy is equal to -1, the coefficient of B4 is -1, so we get minus B4. Again, we have, for the bending motions, we're going to have a doubly degenerate EU motion. So here we have x comma y. This tells us that we have two different basis functions that are doubly degenerate. So first, let's figure out what the vibration corresponding to the x basis function is. So we take the value of the x coordinate, plug it in to the function, which is simply x, and that becomes the coefficient for B1, B2, B3, or B4. So since x is equal to 1, the coefficient for B1 is simply 1, so we have B1. For B2, x is equal to -1, so the coefficient is -1, so we have minus B2. For B3, x is again equal to -1, so the coefficient is minus B3. So we notice it's not the same as the B2G bending motion. And then for B4, the value of x is equal to, again, 1, so we have plus B4. So we have B1 minus B2 minus B3 plus B4, and this is the bending motion corresponding to the x basis function. So now we can do the y basis function independently of it, which we note as a contrast with the projection operator method, where it's a involved process to get the second member of the pair, the partner function as we call it, the other member of the pair, from the first member. It's difficult in the projection operator method, whereas in the Kim method we can define each of them independently of the other. So using the y basis function, we look at the value of the y coordinate, and that becomes the coefficient for B. So y here is 1, so we have plus B1. For B2, the coefficient is going to be plus 1. Here the value of y is minus 1, so we have minus B3. And then for B4, again, y is equal to minus 1, so the coefficient is minus B4. So again, we have both members of the doubly degenerate EU pair that we were able to determine independently of each other. Next, we want to draw what each of these vibrations looks like. So for example, we start with A1G, and we notice that the function that we were able to derive was R1 plus R2 plus R3 plus R4. Using our nickel chlorine diagram here, this is equivalent to all four of the bonds getting longer at the same time. And one of the ways that we represent this is to show a directed arrow from the center out to the outer atoms. If it's pointing towards the outer atoms, that is the bond getting bigger. If we were to have an arrow pointing from chlorine to nickel, that would be the bond getting shorter. So for A1G, we see all four bonds get larger simultaneously. Next, we have the B1G. And the function for B1G is R1 minus R2 plus R3 minus R4. So again, we can draw a sketch of what this vibration is going to look like. And we recall the numbering system that we use for the bonds. So this particular bond gets bigger because it's a plus R1. Now we have minus R2, so we often do this and show the vector going back towards nickel. This is as this bond gets bigger, this bond gets smaller. R3 gets larger, so we show a directed arrow from nickel to chlorine, and then R4 gets smaller, so we show the arrow going from chlorine to nickel. Remaining for the stretches, we have the EU pair. So recall that the first pair, corresponding to the basis function x, we're able to write as R1 minus R3. So let's see what that looks like with a quick sketch of our molecule. So we notice that R2 and R4 are not mentioned at all. So they stay exactly the same as they would. So one way to represent that is as a line segment going from one to the other but not directed. So we don't have an arrow. We have R1 gets bigger. So we can show our directed arrow from nickel to chlorine. Whereas R3 gets smaller, so the directed arrow goes from chlorine to nickel. So this is a way to represent the EU stretching vibration that corresponds to the x basis function. Then for the y basis function, we have R2 minus R4. So again, we can draw it. Quick sketch. We notice that R1 and R3 are not mentioned. They have coefficients of 0. R2 has a positive coefficient, so we draw it as a arrow in this direction that's getting longer, and R4 is getting smaller. So we see in this case, in D4H, the two partners, the two pairs of doubly degenerate functions, it's rather easy to notice why they would have exactly the same energy. We have two bonds that stay the same length, one gets bigger and one gets smaller in both cases. So this is a case where the degeneracy is relatively easy to notice, whereas in some cases, such as in D3H or C3V, it's often very difficult to predict a priori what the other partner function would look like if you just know one of the pair of doubly degenerate functions. Next, we have the bending motions, and recall that one of the bending motions was a B2G, we found that we could describe this by the function B1 minus B2 plus B3 minus B4. So we want to see what this looks like. We draw our ion again. And we notice that the bending angle 1 gets bigger as angle 2 gets smaller. So we can think of this as getting bigger in this direction. 3 also ends up getting bigger as 4 gets smaller. So 3 gets bigger and 4 gets smaller. So we see that even staying in the plane, this angle here gets bigger, this one gets bigger. At the same time, this one gets smaller and this one gets smaller. You also have 2 EU bending motions. We call it the first one corresponded to the x basis function, and that was B1 minus B2 minus B3 plus B4. And we want to see what this would look like using the same diagram, so we don't have to draw it again. Let's see what we have here. So we have angle B1 getting bigger. So we draw it the same way we did before. It's one way to represent the angle getting bigger. And B4 also gets bigger. So this one and this one both get bigger, whereas B2 and B3 get smaller. So you can see this one gets bigger simultaneously as this one gets smaller and this one gets smaller. Now for the y basis function, we have B1 plus B2 minus B3 and minus B4. And let's see what this would look like, again using the same diagram we have here. So angle 1 gets bigger. Angle 2 also gets bigger at the same time, whereas 3 and 4 here get smaller. So this one gets bigger, this one gets bigger, this one gets smaller, and this one gets smaller. We were able to derive 7 of the 9 vibrations easily for this particular ion using the Kim method. The other 2 vibrations can be derived by the Kim method, but they involve a certain amount of extra theory, which isn't particularly appropriate at the moment. I thank you very much for your attention. Have a good one.